How are you? How was your exam? Can anyone please reply? How was that exam? Means it was very tough or it was very easy? And I have seen 2 to 3 sheets. I have not seen all sheets, but I find few people they have written very well and they have answered all the questions very clearly, and they have mentioned in the numerical segment actually that they have clearly mentioned each and every part. Okay, and for theory I find very less people they have written very clearly in the theories, because I asked, I think 3 theory question was there. You while writing in that theory examination, just write what you have read in conceptual thing, means what is in your notes, because if somebody will ask that what is the Pascal's law, I think I have given that Pascal's law, so definitely write to the point. I find 2 or 3 candidates they have written, I don't know from where they have got that literature, they have written not in exact manner. Okay, so good morning everyone, and today is the after a long gap near about 10 days we are going to start our bioprocessing 1 course. So as yesterday there was one meeting with academic persons, they told that we will have to give a overall glimpse of whole subject, like what we have covered up to till date, and for 3 to 4 lectures we will be discussing that which topic we have covered and how you can implement in your further studies or further training as well. So first of all we will talk about, okay, I think before going to that lecture, first we will discuss that am I audible before starting? Am I audible? Yes or no?
Yes, sir.
Okay, thank you. So before starting to anything, I think you have read all the syllabus. Let me open your syllabus copy as well. That in your syllabus, the first unit which is belongs to your fluid mechanics, you see, and here we have covered, I think, near about complete topic. There is nothing left till date for unit 1 if I am talking about. And we have thoroughly discussed that what is the viscosity, what is the Newton's law of viscosity, and I have given one question regarding your kinematic viscosity and that the dynamic viscosity. I found 2 to 3 people, what they did, they can't even calculate that area in wait, I think here I have given each and everything. By using this dimension you have to determine the area and you have to determine your tau, and you have to do nothing, just directly apply the Newton's law of viscosity and divide with the density. That is very simple question. Okay, and we have covered Rheological diagram, where we talk about how many types of fluid, like Newtonian, non-Newtonian fluid, and we have also discussed about Euler equation and its application. We have discussed, and derivation of Bernoulli's equation from Euler equation. We have also discussed this derivation. I think I have given in your test as well. Application of Bernoulli Theorem, we have already discussed that each and every your flow measuring devices like Venturi, orifice, rotameter, each and everywhere this is applicable. And Pascal's law, I think I have given this in your test, that examination, but I found few people they have written very clearly. And yeah, and hydrostatic law, same thing, and measurement of pressure, like gauge pressure, absolute pressure, we have already discussed. Barometer, we have already discussed this thing, that how we can determine the pressure by applying normal what will be the change in the height into that liquid, that by the application of that height we determine that your pressure. nothing but it is, if you'll apply the P equal to rho g, very famous formula, very famous. P equal to rho g h. H will be the height, how much is the change in the height, G is your gravitational force, 9.8, and rho is the density of liquid or water, whatever you are using, and various type of various type of manometer to determine the pressure, piezometer, YouTube manometer, single column. And this theory part I have not given your examination because this is very theoretical, and their application as well. I think this whole unit we have covered. Okay, so we will talk about little bit glimpse on 3 lecture. We will talk about unit 1 today, and then in the next class we will talk about little bit about the unit 2. I will try to cover. If anybody if feeling he couldn't understand in the unit 1, he can ask anything. Okay, so we will go to directly to our notes first of all, that what we have read till date. And one more thing, I think some people can, okay, I will discuss between in this class. Okay, leave it. I think we will start from your lecture or lecture 1. That in the first lecture we have discussed about that how the bioreactor, that which is nothing but it will be the like a CSTR reactor. CSTR means continuous stirrer tank reactor. What we are looking for, when you will fill this whole reactor with liquid or any kind of solvent, when you will add any kind of microbe or algae or anything, any biological living organism, when it will grow, its flow characteristics and flow dynamic will change, because this thing will be depend on your dynamics. This propeller, impeller, whatever, it will rotate and it will enhance the mass transfer into the liquid. And the third one, in the second one, we are looking for how much mass is transferred into that liquid. So to determine such kind of system or to design such kind of system, we have to look into how the fluid behavior changes into your reaction system. So we have discussed that we have talked about that how the fluid property is changing into that system. Here definitely, if you will add any kind of living organism, it will enhance the turbidity. Turbidity means your solution will be like thick solution, because it will, at the initial stage it will be clearly visible, but after some time it will become hazy due to the formation or the growth of your microbe or any kind of algae or any kind of living organism. So this in the designing part, if you are talking about the designing part, definitely you will have to know that how the fluid or any kind of liquid or any kind of solvent which you are adding, because in your this inoculation system or in your solution, there is a lot of things you are adding, like glucose, you are adding any carbon source like any kind of carbon, glucose, sucrose, fructose, it can be anything. You are adding any kind of minerals, a lot of minerals like iron, magnesium, Mg, and Mn, all these minerals to grow your microorganism. So definitely you have to look into how these minerals or how these all the minerals it is behaving into liquid system. So before going to the designing part, definitely you will have to look that how the fluid property it is changing into your reaction system. So we have discussed that how the fluid is different from your solid particle, like different from solid and gases. So we have talked about that if you have any kind of tube, if the fluid is flowing from this direction to this direction, then what you are looking for, you are looking for how the fluid is changes into this particular region, because this is the substantial or very smaller infinitesimally small fluid element that which will flow into that liquid system. Then you have to look into its physicochemical characteristics. For that, if the plate is stationary, the fluid will be laminar, and here you could not find any kind of turbulence, then this picture will be, you can easily see. Now if you will apply some kind of force here, you have applied some kind of force, any kind of force, then here will be the deformation takes place into your liquid system. And in the deformation, if you are talking about the velocity changes, how the velocity will change if this is your flowing element, you have cut this slide from here to here, and you will find that it will change, the moment will change from this direction, means this much has been changed due to applying this much, position of the fluid has been changed due to applying some kind of forces. And definitely it will be depend on your time, means up to what time, up to how much time you are applying these forces to study this kind of phenomena, because you will pass through liquid or any kind of solvent through any kind of pipe. And to enhance the mass transfer, what we are doing, we are generally looking for turbulence condition, because when you will add a liquid in turbulence condition, more and more mass transfer will be generated into your reactor inside your reactor system. Okay, so if the fluid will pass like this, you can see from the plate 1, plate 2, here you could not see any kind of moment, but here you can find little bit of the moment in this direction. If we'll check that at varying the time, the element of the fluid, that this particular region of the fluid will shifted from this position to this position, this position, from T0, T1, T2, T3. So definitely you have to determine that, you have to define the how the fluid is changing. For that, if there is the liquid, no problem, because if small applying force, it will uh, uh, it will accelerate the fluid into forward direction. But if you're talking about the solid particles, solid will, you have to apply enough forces to break is elasticity, means definitely there is one term called as the elastic limit. You have to break that force, then only it will shift. Now the very famous this condition called as the no slip condition, the fluid mechanics generally people use this kind of boundary condition, means you are assuming that here will be no slip condition, means velocity will be at the surface will be zero. But if somebody will say that here is the slip condition, means there will be some kind of velocity, uh, yeah, some kind of velocity. Now here similarly for plate 1 as well, here if the fluid is flowing through the pipe, if the fluid is flowing over a plate, now see how it will change. Here will be if the no slip condition, it will go up in this direction, and here the velocity will be changes in y direction. But here you are assuming the no slip condition, means surface velocity is zero. So these fundamental theory, just keep this in mind while designing, while studying the, if you are dealing with the liquid, this thing is very famous while while deriving, if you're deriving any kind of fundamental Newton's law of Navier-Stokes equation or Eulerian equation, then you have to keep this in your mind. Now, if you're talking about the basic equation, first will be the conservation of mass, Newton's second law of motion, the principle of angular moment, first law and second law of thermodynamics. I think you already know this thing. Conservation of mass means you are assuming there will not be any kind of losses into your reaction system. Newton's second law of motion, F equal to ma, and first law, second law, and principle. All these things I think you might have read in your 12th standard. So I'm not discussing this thing. And there is one more thing in the that zeroth law of thermodynamics is also there. Okay, now for deriving any kind of application, so three things you have to keep in your mind as one will be your free body diagram, second will be your system, another one will be your control volume. If you have any kind of system where the fluid is flowing, then definitely you have to keep in your mind while deriving, if you have any kind of system which is flowing, then you have to define at what particular position you are taking your segmental or substantial derivative. Like if you're talking about this particular region, fluid is flowing from this direction to this direction. If you're talking about this particular zone, you have to define these three terms. One is your free body diagram. Free body diagram means you are defining your elements. You are defining your elements, this thing, in a particular region. So this thing defining this free body diagram. Now the second is your system. System means call as the where you are looking for, or which if any kind of reaction which is happening in your system, then whole particular region which is called as the system. Okay. Third will be the control volume. Control volume means how much volume occupied, means this particular from the boundary of this thing, this whole boundary which is called as the control volume, means inside this boundary how much the fluid element is present, this thing whole. And to define the fluid volume, generally people call as this particular region called as the fluid surface. Around the surface of the control volume called as the fluid surface. Okay, these things we have already known. Now there is the few example. Now have a look. If we're talking about the piston, which is generally used in your bikes or any kind of combustion system, now see, this is the whole particular region. Here is the piston and cylinder will be there. This is your cylinder, this is your piston. When piston will compress any kind of fluid, any kind of your diesel, petrol, oil, then the combustion will take place. Then what will happen? When it will compress this particular region call as the system boundary, or you can say the control surface. And this particular region where the whole substance or your diesel or any kind of petrol or any kind of liquid will be present, this particular call as the control volume, the whole volume inside your system. And similarly now see here, if this is the T-shape structure, which is generally, if you will read in computational biology means when your it is generally applied for, you can say, the biological people, where the fluid will flow from this direction to this direction, this direction to this direction, any direction. If the fluid is coming in your body, then generally people look into how the turbulence, how the mixing which is happening in the T particular region, T region. Because if the one fluid is coming, there is a lot of segments are there. Let me make few. Like there is the T shape. T shape means T, complete T will be there. And if the bended T like this, that which this figure, and there is the jet shape, means this particular region, this here, if the fluid will go from here to here, you are adding any kind of liquid from this direction, then here will be mixing will happen. Same thing, if the fluid will go from this direction to this direction, then here will be mixing will happen. So generally bio people or biological student, they are looking for how the fluid or how the mixing which is happening in this direction. Because when a doctor inject any kind of fluid in your body veins, it is generally used at an inclined angle, not in a 90 or any kind of angle. He inject any kind of injection in near about not exactly 30-40, but near about in inclined angle. Why? When he inject this thing, if the fluid is flowing from this direction to this direction, this injection, if it is injecting from this particular region, this, it is not in like this. If the fluid is flowing this is your in, this is your out. If doctor is injecting here, now this particular angle, this angle of injection will help to flow your medicine or your that the substance which you want to inject in your body, that will flow continuous manner, and it will go with your that flow of the veins, that the blood, sorry, flow of blood into your veins. Same thing which is applied, we generally simulate. If you will find, there is a lot of research articles also there to how you will design the good T joint, Z joint. There is various type of joint. Y joint, Y joint is there, very famous Y joint. Generally people do like this. This is your Y joint. Fluid will come here, and this direction, and how it will behave. These are the real life examples that people do simulation, and how the injection or how the liquid will flow into your body. Same thing which is happening in your veins as well. So, and this thing we I think you can read at higher study in your computational biology. And here we also solve one example by here. Definitely, if you'll apply the continuity equation a1 v1 equal to a2 v2, while assuming density is constant, rho a1 v1 a2 v2, you can easily determine that velocity. If you know the velocity at this point, we have, I think, solved this thing in your classroom when we were in physical classroom, and we have solved how the velocity, we have determined the velocity at this point. Okay, same thing. So we will not solve this problem. We have already solved. Now, the fluid is continuum. I think we have discussed one lecture on this. That fluid is continuum means we are assuming that fluid or any kind of in the property inside the fluid will be continuous throughout the position and the time. Means any kind of property like density, viscosity, or temperature, any kind of viscosity will be continuous throughout your reaction, throughout the fluid. Means if you have any kind of fluid element, if somebody will say that fluid is continuum, means each and every property, your density, your temperature, your velocity, each and every property inside the tube will be constant. This is called as the continuum. The one word justified each and everything, continuum. Generally we assume for the steady state condition. Means fluid, we are assuming while deriving that fluid is steady state, but in real scale application fluid cannot be at steady state condition. But we are assuming that each property, density, viscosity, and any kind of physicochemical property will be the function of space and position. So this is the fluid continuum theorem. And I think here we have also written that density is the function of, we have given some example like density is the function of x, y, z, and t. These are the positions, x, y, z, three positions, three dimensional, and t is your time. This is your position, this is your time. Okay, now the velocity, similarly for the velocity term. Now moving towards, we also discuss streamline, streak line, and path line. But this thing we have not, we have read few things little bit about that this thing, because this thing is not too much in your flavor. That's why I have not discussed this thing, because as a chemical engineer, generally people use this kind of theorem in deriving and solving the numericals. But in your curriculum it is not in too much depth. So we will talk about little bit about that the timeline, straight line, is streamline, path line, straight line. But just keep this thing in your mind that this thing is applicable where the fluid will flow. First of all, very famous that timeline. What does that mean? The timeline means when the fluid element, any kind of that, here you see the picture, when the fluid element, any kind of, if you will, fluid will be here, which path it is following, this is called as the timeline. Means it will show some kind of trajectory or some kind of positioning, that it will go here and here and here. Then all the position which will be shown by a particular fluid element, which is called as the timeline. And path line, if you will draw this line at a particular direction, if you will draw, if the fluid element going like this, if you will draw, this is called as the path line. Means it is following some kind of path to represent the whole fluid motion into that channel. Okay. And a streak line means if you have any kind of region like this, you have any kind of region, if all the fluid element will cross through this segment, this particular region, means fluid will come here and it will cross through this particular zone. This is called as the streak line. And if you're talking about the streamline, which is defined as tangent to the flow. So these four theories just keep in your mind, because these are the very simple and very fundamental as well. When you will solve your problems based on tangential problem, means how you can derive or how you can plot the tangent of the flow, any kind of flow. So this thing you have to derive, means if you define del u by del x or del u by del y, it will give the any kind of positioning, and you can easily determine your how that the streamline will be, how it will look like. Okay, and one more thing, we have solved one problem as well. Yes, now you can see tangent, it is nothing but dy by dx. I think you know this thing, y1 minus y2 divided by x2 minus x1. It will give you the slope, and you can easily determine your uh, the position of any kind of element, or you can derive the expression in the equation we have talked about now, that if any kind of fluid element which is flowing from here to here, then how you will define the trajectory of the equation, how will derive, means how you will determine the position. So for that, if you will derive the expression based on function, any kind of function will be x and y. If you'll get any kind of equation, then you can easily determine the position of the fluid element which is flowing from this direction to this direction. We've already discussed this thing as well. And now the what is the viscosity, we have to definitely, if any kind of fluid which is very thicker, generally people tell that this fluid is very thick, means it is highly viscous, like your honey. When you will compare with your water is less viscous as compared to honey. So to define this kind of property in physical appearance, it is okay that you can easily see with your naked eyes that the honey is very viscous and water is less viscous. But how you will define that viscosity? So to define this thing, we have to write the expression, and we have to see how you will justify that viscosity. So here we have discussed about the Newton's law of viscosity, means any kind of fluid which which is proportional to the rate of deformation, you can easily determine, you can easily define which kind of fluid it is. Okay, so to define this thing, same thing, you have taken any kind of fluid element in this region. What will happen when you will apply any kind of force? This much amount has been deformation takes place, or you can say the change in angle delta alpha. Then how you will determine tau, force per unit area. This is the fundamental thing, that how much tau is nothing but, means it defined how much force you are applying per unit area. Same thing. And rate of deformation, how much is the change with respect to time, this particular change. How much is the change in angle, then how much it will be depend on your time, del alpha by del t. Similarly, then to define this thing, what you have to do, you have to determine how much is the change in delta L. How you will determine delta L? I think I have written here, delta L equal to velocity multiplied by time, and delta L will be delta y and delta theta for very small angle, because as I already told, this theta is very small. We are assuming for ideal condition. Keep this in mind, steady state and ideal condition. When you will compare, you will get the expression for del alpha by del t. It will be nothing but del u by del y. Just put these values and compare, you will get the expression for rate of deformation. Okay, I think we have not written, but tau will be proportional to del u by del y. Okay, rate of deformation. Okay, now here we have now you can see the relationship between the shear stress and shear strain. The fluid in which the shear stress is directly proportional to the shear rate or deformation, called as the Newtonian fluid and non-Newtonian. Yeah. We have already discussed in your that Newton's law of viscosity, that if the tau is proportional to your del u by del x, let me write tau proportional to del u by del y, then this will call as the Newton's law of viscosity. Means it will proportional to that rate of deformation. Sorry, this is rate of deformation, shear stress proportional to the shear strain. Then this is called as the Newton's law viscosity. We have also derived, like now you can see, tau yx equal to, or sorry, proportional to del u by del y. Okay, we have already discussed this part also, that tau yx, how we are writing tau yx. Let me repeat, that velocity which is changing, it will be in your x direction, and that the change where it is happening into y direction. Same thing. Now see, if you have any kind of element, now you see here, if the fluid is flowing in this direction, what will happen? You are applying some kind of force in this direction, velocity in this direction, then change is happening in upward direction, y direction. So it will be depend on tau yx proportional to del u by del y. This is called as the Newton's law of viscosity, where the shear stress is proportional to your shear strain. Okay, so if you equate both things, the one constant will come which is called as the mu, which define your viscosity. And in the layman language, how you will define the viscosity means how much shear force applied by one layer of fluid to the adjacent layer of the fluid. Generally people talk in the term of the layers, like if you have one layer here, one layer here, how much force exerted by this fluid portion to this particular fluid portion. Okay, we are looking for how much is the shear stress, or how much is the resistive force applied by one plate to the another plate. This is called as the viscosity. Okay, and we have the unit of the viscosity. Similarly, tau will be force per unit area, and del u by del y you can easily determine. It will be near about Pascal second, and I think this thing I have given in your exam also, that Pascal in the SI unit, and in the CGS it will be twice. And similarly, kinematic viscosity, I've given this problem. You have to divide it by the density. You will get that the kinematic viscosity. For the kinematic viscosity, how you will determine kinematic viscosity? If you divide by any kind of density of the fluid which you are dealing with, dynamic viscosity, it will give you the kinematic viscosity. But there is one thing keep in your mind, if in your question paper, which is, if it is not mentioning that this is the dynamic or kinematic viscosity, then just keep in your mind this will be your dynamic viscosity. Okay, means he's talking about only mu only, he's not talking about nu. Just keep in your mind, if he's mentioning that the fluid which is having this kind of kinematic viscosity, then only assume that this is the kinematic viscosity. Otherwise, generally people talk about dynamic viscosity, how the fluid property changes with respect to time. Now here we have also talked about that, which is called as the one stroke. Generally, kinematic viscosity determined in strokes, and dynamic viscosity determined in twice. And here, very famous Newton's law of viscosity, which state when the shear stress of the fluid element layer is directly proportional to the rate of shear strain. Means when your shear stress proportional to your del u by del y, which is called as the Newton's law of viscosity. This thing mu, that the viscosity, this particular term define your viscosity term. Okay, and one thing here, for gases, viscosity increases with temperature, and for liquid, viscosity decreases with the temperature. Just keep this in your mind, because in your interview, I think I have find various time that people, they are asking itself, I have faced the same problem. One faculty was asking about me how the viscosity will change. Then he told me just derive the formula, just derive the expression. I think you know this formula, you know this method, that del u by del y, this thing. Then after that, what he asked, I was surprised that he was asking about just note down the equations. Then I have written the expression, and he told just derive the Newton's law of viscosity by your substantial derivative. So for that, we generally, what we are doing, we are generally writing that mu, sorry, tau will be proportional to del u by del y. But he was talking about that how the fluid will change, because each and every point, if you are talking about this is the function of temperature, then here each and every element here, now the curve nature which is changes, you cannot claim at a particular position, you cannot claim for whole curve standing at a particular position, means each and every point which is changing, your curve is changing, you cannot predict this thing. So for that, you have to write, you have to apply the substantial derivative. You cannot apply this kind of formula because this is the straightforward formula. If you will look what you are doing in your numerical solving, if you have any kind of fluid, here is the fluid, the upper part have some velocity near about 10 centimeter per second, 10 centimeter per second. It is moving in this direction. Okay, this is stationary, zero, no slip condition, no slip condition. Okay, but he told that if your velocity, now how it will be velocity profile like this, you cannot write this expression for this particular reason, because you see each and every point the position of the fluid element which is changing. So you, for that you have to apply that the substantial derivative. You cannot apply generally what people do, generally everyone is doing same thing, that how much is the velocity at this point, okay, here baba 0 and here is some velocity like 10 meter per second, just subtract both point, 10 minus 0, 10 minus 0 divided by how much is the thickness, how much is the length of that pipe. If it is 1 meter, then 1 minus 0, then you have got the del u by del y. But this is not the correct answer. If somebody will ask, just note down the that the Newton's law of viscosity, just write tau equal to proportional to the del u by del y, but you cannot predict for the whole position. But in numerical solving, we are generally doing del u by del y. Just keep this in your mind that this term is very dangerous. If you are solving or if you are sitting for interview, to keep this in your mind, this you are claiming that how much is the distance from this position to this position, but it is not true, because it is changes throughout the position, it is changes throughout the position. So you have to apply substantial derivative. Okay, and one more thing, if you will definitely, if you will apply any kind of temperature, your viscosity get reduced. Okay, but in the gaseous it is happening inversible, means if you will increase the temperature, the viscosity, if you will increase the temperature, viscosity will increase. Just keep this in your mind. Why increase? Because there is a lot of, I think you might have, you maybe know Brownian motion. If you have any kind of closed container, if you increase the temperature, here the molecular particle moment, it will enhance, so much. Due to that, this position get increased, because it will create so much chaos at this particular whole region. So it will enhance little bit viscosity, not too much, a little bit viscosity, because in the gases you cannot predict that it will enhance or it will reduce so much, it will increase a little bit. Okay, I think you have got this idea. And similarly, non-Newtonian fluid, we have discussed one plot, that rate of deformation and shear stress, and this term called as the Newton's law of viscosity. And here the dilatant, pseudoplastic, Bingham plastic. Just read all the examples of that. The Bingham plastic is very famous, like your toothpaste or any kind of muddy solution. which comes in the category of the Bingham plastic, because after some time it will behave like a Newtonian fluid. But here is the little bit difference. This position, this rate of deformation means this much amount of force or this much amount of energy you have to apply to move the fluid in forward direction. Now, okay, similarly, and one more thing, to determine or to define the physical property, we generally, for Newtonian fluid, we are applying Newton's law of viscosity, but to define this thing we use power law model, very famous power law model. If you are dealing with any kind of non-Newtonian fluid, what are the non-Newtonian fluid? Any kind of fluid it can be, like CMC, carboxyl methyl cellulose. If it will mix into the water, it will behave non-Newtonian fluid. If you will mix any kind of cell or any kind of microbe in your reactor, in your that the liquid system, definitely it will behave the non-Newtonian fluid, because the property which is not continuous with respect to time, it can predict, it can change any position, means it can change anywhere. If you have this reactor, you cannot predict that fluid property which you have added into that reaction system will be same throughout the reaction system. So what you are doing, that stress or any kind of force you are applying into that system, that it cannot be proportional to that the rate of deformation tau, it cannot be proportional to the deformation rate, this thing. So generally we are applying power law model. What does that mean? We are adding one more term. How we are adding one more term? Tau will be, and I think you know this formula, correct? This formula is y equal to a x power b. A is your constant, b is your constant, but it can modify, it can give the same result as the Newton's law of viscosity, but you have to modify it. Means a you have to assume as mu, then only it will look like similar to the kind that the Newton's law viscosity, and b will be your 1, then only you can claim y equal to a will be your mu, and x will be the how much the deformation rate, then it will be del y by del y, same thing. Okay, just keep this in your mind. It is nothing but it is the expression that you are deriving from Newton's law of viscosity, or you can say the power law model for the Newton's law of viscosity and non-Newtonian fluid as well, both type of fluid, Newtonian and non-Newtonian fluid. For non-Newtonian fluid, you are adding one apparent viscosity, one more term, apparent viscosity. Now you can see you have taken one term common from this particular term, and this whole term called as the apparent viscosity, which is neta. And this thing, this particular, I think this use to determine where is the time dependent or time independent fluid come into the picture. Now you can see if the eta is less than 1, what will be? It will be the pseudoplastic. Okay, the apparent viscosity decreases with increasing deformation rate. If the eta is higher, it will be dilatant. Dilatant means the apparent viscosity increases, not decreases. Here it will increase dilatant with increase in the deformation rate. See the example, suspension of a starch and sand, same thing, but here the polymeric solution. Means if you increase the deformation here, the viscosity will decrease, but here it will increase. You cannot predict that. If you apply some kind of force to the sand, that it 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 may be moved forward, but it will be depend on the force as well. So but in the polymeric solution, if you apply any kind of force, it will move forward. Same thing for the colloidal suspension and the paper pulp in water. Okay, and this is for the Bingham plastic. Bingham plastic means tau yx, and here this particular force you have to apply extra as compared to Newtonian fluid or Newton's law of viscosity. This, if you will delete this particular zone, then this is the same formula of the Newton's law of viscosity. Tau yx equal to mu del u by del y, same formula. But here you are applying some additional force to behave the fluid like a Newtonian fluid or Newton's law of viscosity. Okay, here is the examples like toothpaste, very famous thing, and drilling mud, any kind of muddy thing, or clay suspension. These things come into the category of Bingham plastic. Just keep this thing in your mind that Bingham plastic, anybody will ask, okay, there is some kind of fluid which shows, which can predict the similar behavior, but it requires some additional force, which is called as the Bingham plastic. Just keep this example in your mind, toothpaste, because everyone is using this in your day-to-day life. So this is the Bingham plastic toothpaste. And here another classification like time dependent, time independent, time dependent, thigmotropic, rheoptic, and viscoelastic fluid. And this is generally people use for the research purposes, not for you too much. But rheoptic fluid which generally used for you, like you will add any kind of microbe into that reactor system, then it will change, the turbidity will change, the color will change. So to define, we generally look into that, the how the viscosity has changed and how the property has been changed. Okay. Okay, so we have finished this thing, and on Monday we will discuss this thing. Okay, that Bernoulli's theorem, Euler equation, and its derivation and its application. Okay.